Hello, everyone. In this section, we will introduce DC circuit analysis for bipolar junction transistors, or BJTs. This is the introduction to Case 1. From the previous section on the operating concept of BJTs, we know that a BJT has 4 operation modes. These modes are determined by the bias conditions of the base emitter PN junction and the base collector PN junction. In most circuit applications, a BJT operates in active mode, while some cases operate in saturation mode. This slide summarizes the device characteristics of NPN and PNP BJTs in active mode. For both types, IE equals IB plus IC. Also, IC equals beta times IB and also equals alpha times IE. Here, alpha equals beta divided by the quantity 1 plus beta, while beta equals alpha divided by the quantity 1 minus alpha. In active mode, beta is usually given as a device parameter. For an NPN BJT, IC equals IS multiplied by the exponential of VBE over VT. Here, VBE over VT is inside the exponential term. For a PNP BJT, IC equals IS multiplied by the exponential of VEB over VT. In active mode, the base emitter PN junction can be approximated by the constant voltage drop model, so VBE for an NPN BJT and VEB for a PNP BJT are both approximately 0.7 volts. During circuit analysis, the key check is the collector-emitter voltage. For an NPN BJT, VCE must be greater than 0.3 volts. For a PNP BJT, VEC must be greater than 0.3 volts. Only then is the transistor in active mode. If the BJT operates in saturation mode, the forced beta, defined as IC over IB, is no longer a constant. However, the relation IE equals IB plus IC still holds. The base emitter PN junction is still forward biased and can still be approximated as 0.7 volts. The collector-emitter voltage can be approximated as 0.2 volts. Therefore, for an NPN BJT, VBE is about 0.7 volts and VCE is about 0.2 volts. For a PNP BJT, VEB is about 0.7 volts and VEC is about 0.2 volts. First, let us look at the first case of an NPN BJT circuit. As shown in the figure, both the emitter and the collector of the BJT are connected in series with resistors. In DC circuit analysis, our goal is to find the 3 terminal voltages, VB, VC, and VE, and the 3 terminal currents, IB, IC, and IE. Since most BJT circuits are designed to operate in active mode, we usually start DC analysis by assuming active mode operation. Under this assumption, VBE is approximately 0.7 volts, and the active mode beta value is known. In BJT circuit analysis, the most important starting point is the current path from the base terminal to the emitter terminal. In this circuit, that means the path from the VBB bias node to the negative VEE bias node. We begin by examining the B junction. First, VB equals VBB. Since VBE is approximately 0.7 volts, VE equals VB minus 0.7 volts. Therefore, VE equals VBB minus 0.7 volts. Once VE is found, we can calculate IE. IE equals the voltage across RE divided by RE. The voltage across RE is VE minus negative VEE, which is the same as VE plus VEE. After substituting V equals VBB minus 0.7 volts, we get IE equals the quantity VBB minus 0.7 volts plus VEE divided by RE. After IE is found, IC equals alpha times IE, where alpha equals beta divided by the quantity 1 plus beta. After IC is obtained, the collector voltage can be calculated as VC equals VCC minus IC times RC. Finally, the base current IB equals IE minus IC. At this point, all 3 terminal voltages and currents have been found. Finally, we must check whether VCE is greater than 0.3 volts. If VCE is greater than 0.3 volts, then the active mode assumption is correct and the analysis is complete. If not, the assumption is wrong, and we need to reanalyze the circuit by assuming saturation mode. If the NPN BJT is replaced by a PNP BJT, as shown in the circuit, the procedure is almost the same. We still begin with the base to emitter current path. We first assume active mode operation and use VEB approximately equal to 0.7 volts. First, VB equals VBB. Since VEB is approximately 0.7 volts, VE equals VB plus 0.7 volts. Therefore, VE equals VBB plus 0.7 volts. Once VE is found, we can calculate IE. IE equals the voltage across RE divided by RE. For this PNP circuit, the voltage across RE is VEE minus VE. After substituting V equals VBB plus 0.7 volts, we get IE equals VEE minus the quantity VBB plus 0.7 volts, all divided by RE. After IE is found, IC equals alpha times IE, where alpha equals beta divided by the quantity 1 plus beta. After IC is obtained, the collector voltage can be calculated as VC equals negative VCC plus IC times RC. Finally, IB equals IE minus IC. At this point, all three terminal voltages and currents have been found. Finally, we check whether VEC is greater than 0.3 volts. If VEC is greater than 0.3 volts, then the active mode assumption is correct and the analysis is complete. If not, the assumption is wrong, and we need to reanalyze the circuit by assuming saturation mode. Now let's return to the case 1 circuit using an NPN BJT. If the result from the initial active mode assumption gives VCE not greater than 0.3 volts, then we must reassume that the BJT operates in saturation mode. In this case, VBE is still approximately 0.7 volts, and VCE is approximated as 0.2 volts. We again start from the base to emitter current path. First, VB equals VBB. Since VBE is approximately 0.7 volts, VE equals VB minus 0.7 volts. Therefore, VE equals VBB minus 0.7 volts. Once VE is found, we can calculate IE. IE equals the voltage across RE divided by RE. The voltage across RE is VE minus negative VEE. After substituting VE equals VBB minus 0.7 volts, we get IE equals the quantity VBB plus VEE minus 0.7 volts divided by RE. After VE is found, we use the saturation mode approximation VC equal to 0.2 volts. Therefore, VC equals VE plus VCE. This is approximately VBB minus 0.7 volts plus 0.2 volts, which equals VBB minus 0.5 volts. After VC is obtained, IC can be calculated as the voltage across RC divided by RC. That is, IC equals VCC minus VC divided by RC. Finally, IB equals IE minus IC. Then the force beta in saturation mode can be calculated as IC over IB. For the case 1 circuit using a PNP BJT, the saturation mode analysis is similar to the NPN case. In saturation mode, VEB is approximately 0.7 volts and VEC is approximately 0.2 volts. First, VB equals VBB. Since VEB is approximately 0.7 volts, VE equals VB plus 0.7 volts. Therefore, VE equals VBB plus 0.7 volts. Once VE is found, we can calculate IE. IE equals the voltage across RE divided by RE. For this circuit, the voltage across RE is VEE minus VE. After substituting VE equals VBB plus 0.7 volts, we get IE equals VEE minus the quantity VBB plus 0.7 volts, all divided by RE. After VE is found, we use the saturation mode approximation VEC equal to 0.2 volts. Therefore, VC equals VE minus VEC. This is approximately VBB plus 0.7 volts minus 0.2 volts, which equals VBB plus 0.5 volts. After VC is obtained, IC can be calculated as the voltage across RC divided by RC. Here, IC equals VC minus negative VCC divided by RC. Finally, IB equals IE minus IC. Then the force beta in saturation mode can be calculated as IC over IB. Next, let us use an example to practice the case 1 analysis. As shown in the circuit, we first assume that the BJT operates in active mode. Therefore, VBE is approximately 0.7 volts and beta equals 100. Remember that the starting point is the current path from the base to the emitter. First, VB is directly connected to the 3-volt source, so VB equals 3 volts. Since VBE is approximately 0.7 volts, VE equals 3 volts minus 0.7 volts, which is 2.3 volts. Then IE equals VE over RE, or 2.3 volts divided by 2.3 kiloohms, which gives 1 milliampere. Next, IC equals alpha times IE. With beta equal to 100, alpha is about 0.99, so IC is 0.99 milliamperes. After IC is found, VC equals 10 volts minus IC times RC, which gives 5.05 volts. Since IC and IE are both known, IB equals IE minus IC, which is 0.01 milliampere. Finally, we check VCE. VCE equals VC minus VE, which is 5.05 volts minus 2.3 volts, or 2.75 volts. Since this is greater than 0.3 volts, the BJT is indeed operating in active mode. Now let us use the same circuit, but increase the base DC bias VBB from 3 volts to 6 volts. Again, we first assume active mode operation. Therefore, VBE is approximately 0.7 volts, and beta equals 100. The analysis still starts from the base to emitter current path. First, VB is directly connected to the 6-volt source, so VB equals 6 volts. Since VBE is approximately 0.7 volts, VE equals 6 volts minus 0.7 volts, which is 5.3 volts. Then IE equals VE over RE, or 5.3 volts divided by 2.3 kiloohms, which gives 2.3 milliamperes. Next, IC equals alpha times IE, about 0.99 times 2.3 milliamperes, which gives 2.277 milliamperes. Then VC equals 10 volts minus IC times RC, which gives negative 1.385 volts. Clearly, VCE equals VC minus VE, which is negative 1.385 volts minus 5.3 volts, or negative 6.685 volts. This is less than 0.3 volts, so the BJT is not in active mode. We must reanalyze the circuit by assuming saturation mode. Therefore, we reassume that the BJT operates in saturation mode. Under this assumption, VBE is approximately 0.7 volts and VCE is approximately 0.2 volts. The starting point is still the base to emitter current path. First, VB is directly connected to the 6-volt source, so VB equals 6 volts. Since VBE is approximately 0.7 volts, VE equals 6 volts minus 0.7 volts, which is 5.3 volts. Then IE equals VE over RE, or 5.3 volts, divided by 2.3 kiloohms, which gives 2.3 milliamperes. Since VCE is approximately 0.2 volts, VC equals VE plus 0.2 volts, which is 5.5 volts. After VC is found, IC equals the voltage across RC divided by RC. That is, 10 volts minus 5.5 volts divided by 5 kiloohms, which gives 0.9 milliampere. Finally, IB equals IE minus IC, or 2.3 milliamperes minus 0.9 milliampere, which gives 1.4 milliamperes. Therefore, all three terminal voltages and currents have been found. The forced beta is IC over IB, which is 0.9 milliampere divided by 1.4 milliamperes, or 0.643. This is much lower than the active mode beta of 100. Finally, let's examine the same circuit when the base DC bias VBB is decreased from 3 volts to 0 volts. If VB equals 0 volts and we try to force VBE to be 0.7 volts for forward conduction, then VE would have to be 0 volts minus 0.7 volts, or negative 0.7 volts. That would make IE negative, which is opposite to the expected current direction of the BJT. This means VBE cannot reach 0.7 volts in this bias condition. In other words, there is no significant conduction current. Therefore, IE equals 0 milliamperes, and the BJT is in cutoff mode. This concludes the introduction to DC circuit analysis for bipolar junction transistors, or BJTs, Case 1. Please look forward to the next lecture. See you next time. Bye-bye.